Now let's solve some equilibrium problems. The first problem is you have 2 moles of NO2, a reactant in gaseous phase, and 1.6 moles of N2O4 in gaseous phase in 4 decimeter cube at equilibrium at a given temperature. Calculate K equilibrium, so we only have to plug in and respect the coefficient. K equilibrium is products over reactants. Since they are both gases in homogeneous, just write it as is, except denominator should be squared because of the coefficient 2. Now we just simply plug in. Just remember one note, concentration is moles over volume. So for N2O4, we have 1.6 moles in 4 decimeter cube container. So if you divide 1.6 by 4, that becomes concentration, mole per decimeter cube. For NO2, nitrogen dioxide, you have 2 moles in the same container. So it is 2 divided by 4 squared. Don't forget that because of the coefficient. Once you do that, you have 0.4 in the numerator and 0.25 denominator, and the final answer is 1.6. No unit. K equilibrium has no unit. Second problem, you have sulfur trioxide gaseous mixed with steam, H2O gaseous, giving you a liquid. Now this is the point you have to be careful, and equilibrium. At equilibrium, concentration of sulfur trioxide and water are given, as well as H2SO4, but this information is not needed. It's to trick some of you, so don't be tricked. Calculate K equilibrium. So it is concentration of products over reactant. But since the product sulfuric acid is liquid, its concentration does not change. So we are printing 1. It is part of your K equilibrium calculated. Sulfur trioxide is 0.4. Steam is 0.48. So let's just calculate this ratio and you get 5.20 as your final answer. Question number 3, K equilibrium is given. This is a contact process. Sulfur dioxide gaseous is mixing with oxygen to give you sulfur trioxide. Concentrations of 2 species are given at equilibrium and the third one is being challenged. So let's just write K equilibrium. Homogeneous reaction, so it's products over reactants, raised to their respective coefficient. Since we know what K equilibrium is, we put the value down. Concentration of sulfur trioxide is 11 squared, divided by concentration of sulfur dioxide, which is 4.2 squared, times concentration of oxygen at equilibrium. Now you could use a variable, so I'm going to use X is my concentration of oxygen at equilibrium. So let's just simplify things. 798 is equal to 11 times 11, which is 121. 4.2 squared is 17.64 times X. So X is simply 121 divided by 17.64 multiplied by 798. And when we do that, X comes to life, which is 0.00860 mole per decimeter cube. And X is your oxygen at equilibrium. The next problem, we go this time, you have contact process in reverse, so your K equilibrium is rather 1 over, but we're just going to plug in. So 4 moles of sulfur dioxide and 5 moles of oxygen are present in 2 decimeter cube container. At equilibrium, calculate equilibrium concentration of sulfur trioxide and its number of moles. So let's just write K equilibrium expression wise. They're all gaseous, it's homogeneous, so it's products over reactants. Don't forget coefficient of 2, that becomes your exponent, divided by sulfur trioxide squared. Let's plug in what we know. K equilibrium is given to us, which is 1.47 times 10 to minus 3 is equal to sulfur dioxide is 4 moles over 2 decimeter cube container. So it's 4 divided by 2 squared times concentration of oxygen is 5 divided by 2. 5 divided by 2, no exponent, divided by concentration of the reactant that they're looking for, so it's SO3 squared. So concentration of SO3 squared is simply equal to 4 divided by 2 is 2, 5 divided by 2 is 2.5, so we have, but don't forget it's a squared, so let's just write it as it is. So it's 2 squared times 2.5 divided by 1.47 times 10 to minus 3. Now if I take square root of both sides, then I can come up with concentration of sulfur dioxide. So I'm going to take square root of this side and square root of that side. So simply concentration of sulfur trioxide at equilibrium comes to life, which is 82.5 mole per decimeter cube. Now if concentration was moles over volume, we can say moles is simply equal to concentration times volume, which is 82.5 mole per decimeter cube, multiplied by the volume of the container, which was 2 decimeter cube. They cancel each other out, like terms. Your final answer is 165 moles of sulfur trioxide at equilibrium. The next problem, you have carbon monoxide, steam giving you carbon dioxide and hydrogen gas. First, remember these are all homogeneous, so it's simply you can write K equilibrium, and they're asking you what is that constant equal to. So K equilibrium is simply concentrations of products at equilibrium over concentrations of reactants at equilibrium. Now there are no coefficients, so there is no exponent. We only have to respect concentration, which is moles over volume. So CO2 is 4 moles and the container is 8 decimeter cube. So I do 4 divided by 8. Now hydrogen. Hydrogen is also 4 moles in the same container, so it's also 4 divided by 8. Concentration of carbon monoxide is 1.6 moles over 8 decimeter cube, and concentration of steam or H2O at gaseous is 1.6 as well over 8 decimeter cube. Now the good thing is, since there are no exponents, these 8s cancel each other out. Life becomes simpler. If you don't trust it, you can calculate it. So this is really 4 times 4, which is 16, divided by 1.6 times 1.6, which is 1.6 squared. So when you plug everything in, you are going to get 6.25 as your K equilibrium, or the value for the equilibrium constant. The next problem, now we are going to use ice for this. You have nitrogen monoxide, hydrogen giving you nitrogen, and H2O. As soon as I see the word initially, then I know I need ice method. So I'm going to write my equation, which is 2 nitrogen monoxide, 2 hydrogen, giving us N2 and 2 H2O. I usually make it into a table. There is a plus, there is a plus. First I go after initial values. What do I have for nitrogen monoxide at beginning? I have 0.1 mole per decimeter cube. So initially I have 0.1. I'm ignoring units, so I have enough room to write this equation. Hydrogen is 0.05. 0.1 applies to water, so I write that. And then if I don't have any information, or if the questionnaire is nice and telling me there is no nitrogen, I put 0. Either way, if I don't have value initially, that means there was no nitrogen being injected. Now they wait for equilibrium, but what happens after initial? There is a change. The change goes according to coefficients and left to right. Reactants are being consumed, products are coming to life. So you are removing minus 2x because of the coefficient from nitrogen monoxide. You're doing the same thing to the other reactant, minus 2x for hydrogen. The product will be plus x, and since coefficient of nitrogen is 1, it's 1 mole or 1x. And steam or H2O is 2x. Then there is equilibrium, and they will give me another piece of information usually. They say nitrogen monoxide was 0.062. So I'm going to use it soon, but let's just 0.1 minus 2x is what happens and what's left at equilibrium. 0.05 minus 2x is what's for hydrogen. X is nitrogen, and 0.1 plus 2x is for H2O. Now the other information is saying, look, this is really equal to 0.062. So let me just do a couple of calculations. This minus 2x is equal to 0.062. So what I can say is 2x is 0.1 minus 0.0, I forgot a 2 here, 0.062. I divide both sides by 2. Then I know what x is at equilibrium, and x happens to be 0.019. Now if that's the case, I'm going to put it into all of this, so I have my concentrations at equilibrium and I can calculate. So 0.05 minus 2 times 0.19 becomes 0.12. So this becomes 0.12. This is 0.0119, and this minus this plus 2 times 0.019 becomes 0.138. It's good if you do the calculation yourself. Now we have all the values. K equilibrium is equal to, just respect the coefficient, products over reactant. So nitrogen has no coefficient, is 0.019 multiplied. Steam has coefficient of 2, so it's 0.138 squared, divided by concentration of one reactant, which is 0.062, don't forget that. This is 0.062 for nitrogen monoxide squared, multiplied by concentration of hydrogen, which we decided is 0.12 squared. When you do all that, you will get 6.54. Okay, the next problem, you have this is Haber process, nitrogen plus hydrogen giving you ammonia. Then again, I see initially, so I know I need my ice equation. Let me just write my equation, plus 3 hydrogen giving me 2 ammonia, all gases. So at initial, nitrogen has 0.100. Hydrogen also has the same concentration, 0.100. No information about ammonia, so I know there was no ammonia to begin with. Change takes place left to right, reactant to product, so minus x moles of nitrogen consumed, minus 3 times as much of hydrogen, and twice as much of ammonia, which is x, comes to life. Equilibrium, 0.10 minus x, 0.10 minus 3x for hydrogen, and 2x for ammonia. The next piece of information is they say ammonia at equilibrium has this concentration. So 2x is really equal to 0.0664. So what I can together, X is equal to 0.0332. Now I'm going to put this value and plug it into hydrogen and also plug it into nitrogen. So I have 0.100 minus 0.0332, and here I have 0.10 minus 3 times as much, 3 times 0.0332. Now we are ready for calculations of equilibrium. K equilibrium is equal to product, which is ammonia squared, over reactant, which is nitrogen, times hydrogen to power 3. Let's just put values. Don't forget this is nitrogen, 0.0664 squared, divided by, and when you do this value for nitrogen, you will come up to 0.0678, if I'm not making a calculation error, multiplied by, when you do this calculation, you get 4 times 10 to minus 4, very small number. Don't forget to cube it. Now if you plug everything in, you will get a humongous number, 1.02 times 10 to power 9, which is good for sake of this problem. It was made up, it's not pragmatic. Ammonia is really very lousy equilibrium. You never have a good yield on it, but this is a good problem solver. The next problem is ammonium chloride, a salt of ammonia that is decomposing into ammonia and hydrochloric acid before it touches moisture, so it's hydrogen chloride. They're all gaseous. K equilibrium is given. Initial concentration of ammonium chloride, ammonia, and hydrogen chloride is given. Which way the reaction shifts when equilibrium is established? This is a case that you need your reaction quotient, Q. Now Q is the same connotations as K equilibrium, except this is when the reaction is initially starting or somewhere that might not necessarily be equilibrium. So this is what reaction quotient looks like. Now K equilibrium, the only difference between these two is concentrations are really at equilibrium. So not necessarily the two numbers are the same. If the two numbers are the same, you are at equilibrium. If not, you have to decide which way you're shifting. Are you going toward product or reactant? So let's just plug in and see what we get. So reaction quotient Q is concentration of ammonia times hydrochloric acid. So I have 0.02 multiplied by 0.06. There is no coefficient, there is no exponent. Divided by initial concentration of ammonium chloride, which is 0.50. Now when I calculate this, I will get 0.0024. Now if you look at your K equilibrium is 0.12, so this is less than K equilibrium. Meaning, in order to reach K equilibrium, which is 0.12, what you need to do is increase the numerator, which is products, and decrease the denominator, which is reactant. So I'm shifting to increase my product, so I'm shifting toward the right hand side. So when Q is less than K, we are shifting toward product. If the two are the same, you are at equilibrium, and if it's otherwise, if Q is bigger than K, then you're shifting towards reactant. Because don't forget that K or Q are nothing but products of a reactant, but one is at equilibrium, and that's K equilibrium. One is at any time, not necessarily equilibrium. So be careful with the wording of problem, initial concentration, and stuff of that nature. Finally, the last question, because after this topic I'm going to teach you acids and bases. I have hydrogen sulfate, there is a minus on top, aqueous plus water liquid, giving me hydronium ion, which is indicator of an acid, aqueous, and sulfate ion. A for acids, so K equilibrium could be anything, could be KB for a base, A for acid. It's just indication of equilibrium and attribute of that reaction. This is acidic. Is given to be extremely small at RTP. RTP is room temperature, usually 25 degrees Celsius, and 1 atmospheric pressure, which we also call it standard condition. Initial concentration is given, what is concentration of hydronium at variant. So since initial is given, K is given, I go after ice. Let me write the equation. Hydrogen sulfate plus H2O liquid. I'm going to ignore it, of course, because it's liquid, its concentration does not change that much. So it's part of Ka, H3O plus sulfate ion. At initial, we have 0.1, and we have nothing of hydronium or sulfate. Change takes place left to right, minus X moles of this, coefficient is 1, X moles of hydronium, and X moles of sulfate comes to life. At equilibrium, I have 0.1 minus X, I have X and X. I'm ready to solve. You can solve it quadratically. We discourage you to do that. Actually, IB sometimes penalize us if we do that. Ka, which is 1.32 times 10 to minus 4, is simply equal to X squared, because products times each other. Hydronium times sulfate is X times X, divided by 0.1 minus X. If you solve for X, you know what's concentration of hydronium at equilibrium, which is what they want. Now here you have to write statement of assumption, which is true. If magnitude of Ka is less than minus 3 or smaller than that, you can assume that Ka, and this is how you can write it, is so much smaller than 1 that you can, anything added to X or subtracted from X is equal to that number. So 0.1 minus X is really approximately equal to 0.1. This is our approximation, which is true because of the magnitude being so small. So if Ka is much smaller than 1, X, you will calculate it. I will show you in 5 seconds that it's so small when you subtract from 0.1, you really are not changing that value. So now life becomes easier. So X squared is equal to Ka times this number, which we decided, just minus X, which we decided becomes the number, is equal to 1.32 times 10 to minus 4 times 0.1 minus X, which just became 0.1. If you take square root of both sides, X comes to life, which is hydronium at equilibrium, and it's simply equal to square root of 1.32 times 10 to minus 4 times 10 to minus 1. They are additive, so it's 10 to minus 5. And when you do the calculation, hydronium is extremely small. It's 0.00363 mole per decimeter cube. So our approximation was good, and this is how we want you to do it. If Ka is really small, then make approximation rather than solving it quadratically.